Okay, so now that we have a pretty good understanding of how molecules are put together, why they put together in the same way, we're going to start talking about how we can name the molecules so we know what we're talking about when we discuss them. It'd be real early on in this lecture series we talked about pure substances, and now we can break that down, those pure substances, a little bit further based on our knowledge. We know that if a substance has more than one component, it's a compound. And if it's a compound that's formed through covalent bonds, we call it a molecule. If it's a compound that's formed through ionic bonds, we have an ionic compound. And so we're going to have slightly different naming rules for these two types of compounds. If the substance is not composed of two or more substances, or we can't break it down any further, we know that it's an element, and it turns out that elements can exist in the atomic state, meaning that they're going to form just by themselves. Neon, argon, noble gases are perfect examples of that, and in general, metals are often considered in the atomic state, even though we know that they form metallic bonds. If elements bond with themselves in some fashion, and we've seen examples of that. Oxygen is going to form a double bond to get the octet rule for both examples. We call those molecular elements, and those are found in nature as molecules. And here we can see a table showing the molecular elements. Now you can see that the tan shaded elements are molecules that exist. If they're pure samples, we'll consider them in atomic elements. The elements highlighted in yellow are the ones that are diatomic molecules, which we'll find in H2, N2, O2, F2, Cl2, Br2, and I2. So there are 7 of them. They sort of make a 7 over here, and you've got hydrogen hiding out here. All of those are diatomic molecules, and you have to remember that when you start to use them in chemical reactions. And there are a few elements, phosphorus, sulfur, and selenium, that exist as polyatomic ions, meaning more than 2. A big difference between ionic and molecular compounds is that molecules exist in individual packets. A propane molecule is an individual component. A sample of propane consists of many individual propane molecules, whereas ionic compounds exist in a large array of sodium and chloride ions. It's just not one sodium chloride ionic compound sitting there next to another sodium chloride compound. They're all packaged together in a very large array of cations and anions, and that's what gives it its characteristic crystalline structure most of the time. Okay, so that's where we're going to start off. We're going to start off with figuring out formulas and naming of ionic compounds. We'll start over here. Okay, there's a few short rules for naming ionic compounds, and as you see, we'll do a couple examples, and it turns out to be quite simple. First, you're going to write the symbol for the metal cation and its charge. Write the symbol for the nonmetal anion, then its charge, and as you'll see, there's a little trick where we can switch the signs, and numerical values of the signs will become the subscript for the other ion. If we reduce the subscripts to the whole number ratio, we'll always ensure that we have the correct ionic formula. And of course, a compound or molecule has to have an overall net neutral charge. So the sum of the charges of the cations and anions must cancel each other out. Okay, so here's our little trick. First off, we need to remember that there are many elements, not all of them, certainly not all of them, but there's a lot of elements that we have predictable charges. We know that they are going to either lose 1, lose 2 electrons in the case of 1A, 2A to get to the octet rule. So sodium, lithium, potassium, all the group 1 metals are always going to have one positive 1 charge. Group 2 always have a +2 charge. Aluminum always has a +3. Nitrogen always has a -3, and we'll include phosphorus. The phosphide ion is always 3-. 6A, if they gain 2 electrons, they get the octet rule, and our halogens, if they gain 1 electron, they will have the octet rule. Okay, so we'll start there. Okay, so here we see that if we switch the charge of the cation, it becomes the subscript for the anion, and the same is true if we switch The anion charge becomes the subscript without the sign, of course. We will get the overall formula for an ionic compound if we remember to reduce the whole number ratio. Okay, so let's do a couple of examples. Okay, one of them, of course, you know very well. If we create an ionic compound with sodium and chloride, we know that sodium is +1, chloride is -1. Okay, so +1 comes down here, the -1 comes over here, and that is, of course, NaCl. And I did not want to draw that. We, of course, don't need a charge for our compound. So what do we mean by the charge canceling out? So I usually just do a quick little math. +1 plus a -1, does that equal 0? And of course it does, so that is the correct formula. Okay? Because that's what keeps these together. The attraction between, the electrostatic attraction between the two charges. Okay? So let's do a formula for magnesium chloride, Mg and Cl. Well, we know Mg, magnesium, is in group 2, so that's a 2+ charge. Chloride still has a -1, so the 2 is going to come down here, the -1 is going to come down here, and so that's going to give us magnesium chloride with a 2. And you can see that, okay, if this has a +2 charge, it's going to take two -1 charges to cancel it out. So 2 plus, we'll say +2 plus 2 times a -1 equals 0. Okay? Or if you think about it from the electron transfer standpoint, magnesium is going to give up 2 electrons. Chlorine only wants to take 1, so it takes 2 chloride ions to accept both of those electrons, and now we have the magnesium chloride compound. Okay, one more example. Let's do calcium oxide. Okay, so we know calcium is in the same group as magnesium, so it has a +2 charge, 2 valence electrons it wants to lose. Oxide is 2-. Okay, so we're going to do our subscript switch, and that will give us Ca2O2. Okay, and then so far we haven't used it, but remember there was that rule that we have to reduce our subscripts to our lowest whole number ratio. Since they're both divisible by 2, this turns into a CaO compound, both with 1s. Okay, because you can see that 2+ and a 2- will completely cancel each other out. You don't need 2 of each. So 2 plus a -2 equals 0. Okay, so let's do, if we have enough room, let's try one more. Okay, let's do sodium, let's do magnesium phosphide. Okay, we know magnesium's 2+, and phosphide is a 3-. Okay, so we're going to switch that here, and so that's going to give us Mg3P2. And we can check that math with a 3 times a +2 is +6, plus 2 times a -3 is -6, so that's going to equal 0. So we know we have the correct formula for this compound.